Now, in video 1, you just saw forces being added together to make what we would usually call a resultant force. Right? Add vectors together, right? Get a resultant. It's what they add up to. So here, blue force, blue vector, and green vector add together and make this dotted black vector. So that is the resultant force. If instead you're now after balanced forces, then you want to have a resultant vector which is 0. So all the vectors have to add to make 0. So we don't want there to be a resultant force here. We want something that will balance with these two. So I actually have to think, right, well, if I'm balancing with the green and the brown, and this black dotted is the resultant of the green and the brown, then cancel this out. I just need a force which is in the exact opposite direction. So if I turn this round, this new force I've drawn here, which I could call a balancing vector, that cancels out, or it balances the green and the brown, and it does make sense because look, green and brown are both up. This is a down vector, cancelling out the vertical sum of those two, and green is to the right more than brown is to the left, so the overall vector will be slightly to the right. This black dotted vector is slightly to the left, so it cancels out the horizontal vectors as well. Now, I'm getting there, resultant vector 0, sum of 0. If you like, you could think about it as well, like our old friend, the displacement vectors. If I start out here, in this bottom corner, and I displace this way, then I displace along that arrow that way, and then I displace back along the spotted vector, I'm right back at the start of my journey. I haven't gone anywhere. So those three displacement vectors summed to 0. Right, this is called a situation where the forces are in equilibrium, and this little construction here is called a triangle of forces. The third force there balances the other two, and they are in equilibrium. Sum of the vectors is 0. It's a bit like hanging a weight off of two strings. If the weight is acting vertically, and I've got a red string and a blue string, the vertical components of those two add up to be the same as the weight, and their horizontal components add to make 0 because there's no overall horizontal component. Horizontal component of blue is cancelled out by horizontal component of red. So overall, you've got 0 vertical forces and 0 horizontal forces, which then means there's no overall force at all. Right, one nifty thing that you get, you can do all of your angles and things again. One thing that sometimes comes in and is useful on these diagrams is a little feature called the sine rule. Right, if I call the angle opposite each side of the triangle, theta x is the opposite y is opposite to side x, z is opposite to theta z, and theta y is opposite to y. You get this rule here. It's called the sine rule. The size of z divided by the sine of theta z is the same as the size of x divided by the sine of theta x, and again for y. So it's a little way of working out the size of one of the arrows or the sine of the angle if you haven't got all the information. That works for any triangle, but it's very handy for these sort of calculations. Now, before we go on to the idea of everything being in equilibrium, we have to have a quick look at what moments are. They're turning forces. It's force times perpendicular distance from a pivot. Other word for pivot, fulcrum. Right? If I have this diagram here, the blue force tries to cause a anti-clockwise rotation. The red force tries to cause a clockwise rotation. In this case, my two moments or turning forces are balanced, and that's because force 2 newtons multiplied by distance 2 meters, perpendicular, notice this is right angles. That is 2 times 2, it's 4, and this big clockwise force is closer to the fulcrum. It makes clockwise rotation, and 4 times 1 is also 4. So they're balanced. Anti-clockwise moments are the same as the clockwise moments. That is condition for balanced moments. One thing you come across is this idea of perpendicular distance. If you've got a force at a bit of an angle, then as opposed to 90 degrees, then you don't get as large a turning force. Yeah, obviously, if this force was all the way flat along the beam, it wouldn't make any turning force at all. But here I've set it up so it's at right angles to the pivot point. So if you like, I'm drawing a line from the pivot point to this force. That's at 90 degrees, and that distance there, which I've called xp, is shorter than the ordinary distance x. And if you look at your trigonometry, sine of theta is xp over x. So you can rearrange, and if the moment is force multiplied by perpendicular distance, you can write that it's also force multiplied by x, sine of that angle theta. Of course, if that theta was 90 degrees, theta would be 1. Sine theta would be 1. So you end up with the same, coming back to the same old thing, f times x. Now that comes from xp is x sine theta. Substitute in there. That's for a perpendicular distance. You can, if you prefer, also do it by working out what the perpendicular force is. In this diagram, just done a couple of little construction lines. If that's theta, then that's theta as well up there. So you can say to yourself, oh right, the force, the vertical force is the perpendicular force, and it's going to be the original force multiplied by the sine of theta. So you end up with these two being exactly the same formula. So you can see that sine of theta is also FV divided by F, opposite over hypotenuse. Right? You'll sometimes get questions where they'll give you a whole bunch of moments. They've got to sum to 0. Just be careful. In this situation, this is creating a clockwise moment, right? This is producing an anti-clockwise one, turning that way. This is producing a clockwise, that's producing an anti-clockwise. It matters which way they point, as well as where they are along the beam. Now, lastly, before we finish this topic entirely, the trick with this overall equilibrium, if an object is completely in equilibrium, if all the forces are in equilibrium, then the complete definition of equilibrium is the sum of the forces is 0, but also the sum of the moments equals 0. Classic example, right? If you had a little beam like this, and you had a 5 Newton force up and a 5 Newton force down, the forces are balanced, but they're making an anti-clockwise moment, and it would spin round and round, getting faster and faster and faster. So there, the force was a 0, but the sum of the moments wasn't 0, so it wasn't in complete equilibrium, right? So they've all got to be balancing each other for an object to be in equilibrium. Right, finish.